Hare Krishna. Hope you're doing well. Let's get started with this question on sampling distributions. We are given 20 random random sample of 20 variables from the normal distribution, and based on the first 10, sample mean is constructed, or should I say subsample mean. And also on the first 10, there is this subsample variance also constructed. And with these two statistics and choosing some from the remaining 10 variables over here, there are four constructions given to us, and we have to check how many of them actually match the distribution given, how many of them follow the distribution given. And it may seem like a lot of random variables thrown at us, but once we look at the theory underlying, it becomes very easy to deal with it. Now, when we look at the sample mean, we know that it's going to follow a normal distribution like this, where the mean remains the same as the mean of the given identical and dependent random variables, but the variance is scaled by a factor of sample size. Over here, the sample size is 10. And we know that this thing essentially, which is the sum of squares appropriately scaled by the sigma square parameter, this follows chi-square 9, right? But we should develop this skill or habit of tweaking things LHS RHS way over here as well. For instance, the sigma square can go over here, and when we scale it by a factor of 1 by 9, we get this sigma square by 9. And essentially this is the statistic, and it can be represented like this also. And the intuition behind this is, when we start with something following, say, chi-square, with whatever degrees of freedom, or any random variable for that matter, whenever we say scale it by a constant or whatever, the distribution also gets that factor associated with it. And having this intuition would be relevant with this theory. Now, this is the student's t distribution, where if we have two independent variables, this is standard normal distribution and this is chi-square with n degrees of freedom. Then if we have a structure like this, it follows the student's t distribution. And if we have two chi-square independent chi-square variables with d1 d2 degrees of freedoms, and they are scaled by the degrees of freedom and the ratio is taken, then it follows the f distribution. Now, Snedekor's f distribution. With this theory in mind, we just tackle each of these options very quickly, starting with the first one. Now, this we know is normal mu with sigma square by 10. This is normal mu sigma square, this is normal mu sigma square, this is normal mu sigma square. And the thing is, uh, all of them are independent, right? Because this is a construction of, it's a function of x1 to x10, which is independent from all the other three, which are also independent in themselves. So when you do the cancelling out with the linearity of normal distribution, you will get this distribution. And this we have already seen, by theory it follows this. So essentially this thing, when we scale it by root over q, it is essentially like scaling normal 0 sigma square, uh, this distribution, by the square root of sigma square chi square n, right? Now, if we think about it from this point, this thing, the 31 by 10 and sigma square, that can come out as sigma root 31 by 10, and what remains is normal 0 1, and it is scaled by chi square 9 divided by 9, and the sigma square comes out as sigma. This cancel, and this is exactly what we have. So this is t distribution with degree 9. Yeah, this is actually tn. So t distribution with degree is 9, and with a factors of root over 31 by 10. Similarly, when we look at this other example, sorry, the other question, the other option that we have to evaluate, this is following this distribution and this is following this distribution. So the term given is essentially normal 0 sigma square 11 by 10 scaled by a factor of root over sigma square chi square 10. Now to make it into a structure like this, we can divide by 10 inside the root, which means we'll have to multiply by 10 over here. And again, we can take the sigma square out as sigma, and similarly we can take this entire thing out as sigma root over 11 root over 10, and this thing then becomes 1, right? So now this portion becomes the t distribution structure with 10 degrees of freedom, and over here the root 10 comes down, sigma sigma cancel, so it is root 11 by 10 t distribution with 10 degrees of freedom, which is matching over here. This is correct, this was also correct. The third one is, again, this thing will follow this distribution, it can be checked very easily, and this would be equivalent to chi square degree of 1 with a scale factor of 2 sigma square, and q we anyway know. So the ratio of these two is going to be, these two quantities over here is going to be 2 sigma square chi square 1 divided by sigma square chi square 9 divided by 9. Now to make it into this form, to check if it is fitting this form, this is anyway getting cancelled, and sigma square 1 is the same as sorry, chi square 1 is the same as chi square 1 divided by 1. So this entire thing becomes f1 comma 9, and there's a factor of 2, so 2f1 comma 9, that is also correct. And the last one, when we look at it, it is, this thing is following this distribution, q we anyway know, so the ratio of these two is like normal 0 sigma square 11 by 10, and root over q is essentially root over sigma square chi square 9 scaled by 9. We can take the sigma square out, it becomes sigma. Similarly, we can take this out as well, this becomes sigma root over 11 root over 10, this part then becomes 1. Okay, this is following the t distribution with 9 degrees of freedom structure, but the factor over here is root over 11 by 10, whereas this thing is saying root over 11 divided by 10, not root 10. So this is wrong. Now, this is a tricky area. It may seem like it is right in a moment of hurry, but no, it's wrong. And as I said, very simple, all we had to know was playing around with scaling the distributions and these two, and then we just had to evaluate all of the options given to us, which led us to these three as right. That was it. Take care. Hare Krishna.